Welcome, curious minds, to another deep dive. Today, we're embarking on a really fascinating journey. We're going right to the top, the application layer of networking.
That's right, the part you actually interact with every single day.
Exactly. We're talking about checking your email, streaming shows, browsing the web, all that stuff.
Mm-hmm.
We're going to unpack the concepts and protocols that make it all work using that top-down approach, just like in the Kuros and Ross textbook.
It's a great way to look at it, starting with what you experience first.
Yeah, think of this as your shortcut to really understanding what's actually happening behind the scenes when you, say, click a link or send a message.
And what's amazing, really, is how much we take these applications for granted.
Totally.
But underneath, there's this incredibly sophisticated dance of protocols, different architectures. It's complex.
So we'll explore how these layers interact, hopefully giving you a much clearer picture of this whole digital world.
Yeah, the whole ecosystem.
Okay, so let's start right at the beginning. Why do we even have computer networks in the first place?
Oh, good question. The book puts it perfectly. Network applications are the raison d'etre.
The reason for being.
Exactly. They're why networks exist. Without apps, the network is just wires and boxes.
And think about the evolution. Back in the 70s, 80s, it was text-based email, remote access, file transfers.
Mm-hmm.
Pretty basic stuff compared to now.
Right. Then the mid-90s hit, and boom, the World Wide Web, the killer app.
And since then, it's just exploded. Voice over IP, Skype, FaceTime, user-generated video like YouTube.
Massive multiplayer games, social networking, Facebook, Instagram, Twitter.
And now all the mobile stuff. Location-based apps, mobile payments, instant messaging like WhatsApp. It never stops.
And this constant evolution, it really highlights how applications drive innovation in networking. They demand more speed, more reliability, new features.
Yeah, the network has to keep up.
And a really key insight, something the top-down approach emphasizes, is that these programs run on end systems.
Meaning like my laptop, my phone.
Precisely. Your computer, your phone, maybe a server in a data center. They don't run on the core network devices, like the routers deep inside the internet.
Oh, okay. So the intelligence is at the edges.
Exactly. Confining application software to the edges has been absolutely crucial. It allows for rapid development. You can create a new app without needing to change the fundamental internet infrastructure.
That makes sense. Faster innovation. So, okay, these apps are on our devices. How do they actually, talk to each other across the internet?
Right. Well, first, it's not really the programs themselves talking, but processes.
Processes meaning?
A program that's actually running, an
Yeah.
active instance. So when two processes on different machines need to communicate, they exchange messages.
Okay, messages. Got it.
And typically, one process starts the conversation, that's the client. The other one is waiting to be contacted, that's the server.
The classic client-server model.
hmm
Like my web browser asking a web server for a page.
That's the most common architecture, yes. You have an always-on host, the server, often in a huge data center, servicing requests from many clients. Web, FTP, email, they usually work like this.
But there's another way, right? Peer-to-peer?
Yes, peer-to-peer or P2P. Think BitTorrent. Here, there's minimal reliance on dedicated servers. Applications use direct communication between intermittently connected hosts called peers.
So my computer talks directly to your computer, maybe sharing parts of a file.
Exactly. The cool thing about P2P is its self-scalability. Every peer downloading a file also becomes an uploader, adding capacity. It's cost-effective because you need less central infrastructure.
But I guess there are downsides. Security, reliability.
Definitely more challenging. Decentralization makes those things harder to manage compared to a controlled server environment. And in P2P, a single machine, a single peer can actually be both a client and a server simultaneously in different interactions.
Okay, so processes talk by sending messages. How do they know where to send them? How do they address each other?
Ugh, crucial question. This involves the interface between the application process and the network. It's called a socket.
A socket, like a doorway.
That's a great analogy, yeah. When your program wants to send a message, it basically shoves the message out through its socket door.
Okay.
And to make sure that message gets to the right door on the right house on the right street, you need two pieces of information for the address.
Let me guess. IP address.
That's one. The IP address identifies the specific host machine, like the street address, but a single machine might be running many network applications simultaneously.
Right, like my browser, my email, maybe a game.
Exactly. So you also need a port number. Think of that as the specific apartment number within the building. It identifies the specific process or socket on that host machine.
Ah, So that's why people talk about port 80 for web traffic or port 25 for email.
Hmm.
It directs the message to the right application's door.
Precisely. The web server process listens on port 80, waiting for incoming connections.
Okay, so my app writes data to the socket, address, and port attached. What happens then? The magic internet part.
Hey, sort of. The transport layer takes over. The application hands the message off and trusts the transport layer to get it across the network.
And that's where TCP and UDP come in, right?
That's right. The internet offers two main transport protocols, TCP and UDP. And the application developer has to choose which one to use based on what the application needs.
Needs like.
Well, we can think about the services a transport protocol could offer. First, reliable data transfer.
Meaning, does it guarantee the data gets there, all of it, in the right order?
Exactly. TCP does guarantee that. It checks for errors, requests retransmissions if needed, puts things back in order. Absolutely essential for file transfers, email, web pages. You can't have missing bits.
Makes sense. And UDP.
UDP does not offer that guarantee. It's more like best effort. It sends the data but doesn't check if it arrived or if it's in order.
Why would anyone use that?
Speed and low overhead. For applications that can tolerate some data loss, like streaming video or online gaming or internet phone calls, a tiny glitch is often better than a long pause waiting for a lost packet to be resent.
Okay, loss-tolerant applications. Got it. What else?
Second, throughput. Can the transport protocol guarantee a certain data rate, like guaranteeing you 10 megabits per second?
Can it?
Nope. Neither TCP nor UDP in the standard internet provide throughput guarantees. Some applications are bandwidth sensitive. They need a certain minimum rate to function well, like high-def video. Others are elastic. They just use whatever bandwidth they can get, like web browsing or email.
So best effort on speed, too, basically.
Pretty much. Third is timing. Can it guarantee delivery within a specific time, say, under 100 milliseconds?
We guess no.
Correct again. No timing guarantees from standard TCP or UDP. This is a huge challenge for real-time interactive applications like online games or telephony. They have to build clever mechanisms at the application layer to cope with unpredictable delays or jitter.
Wow, okay. So reliability, yes, with TCP, but no guarantees on speed or timing. What about the fourth service?
Security. Does the transport protocol itself encrypt your data?
Seems important, does it?
Again, no. Neither TCP nor UDP natively provides encryption or integrity protection. If you send data over plain TCP or UDP, it could potentially be intercepted and read or even modified.
Yikes. So how do we get secure connections then? Like when I shop online, the little padlock icon.
That's where Transport Layer Security, or TLS, comes in. It's successor to SSL. Now, here's the interesting part. TLS is not actually a separate transport protocol.
It's not.
No, it's implemented in the application layer, kind of layered on top of TCP. When you connect to a secure website using HTTPS, the S stands for secure your browser, and the server use TLS.
So the application itself handles the encryption.
Essentially, yes. Your application encrypts the data before it even hands it off to the TCP socket. That encrypted data travels over the standard TCP connection, and then it's decrypted by the application at the other end. It provides privacy and data integrity.
Clever. Okay, that clarifies a lot about the underlying services. Shall we dive into some specific application protocols? Like the web.
Let's do it. The World Wide Web runs on HTTP, the Hypertext Transfer Protocol. It's the language browsers and web servers use to speak to each other.
Right, requesting pages, images, all that.
Exactly. Every piece of content on a page, an HTML file, an image, a style sheet, is an object addressed by a URL. And crucially, HTTP uses TCP as its underlying transport protocol.
So it gets that reliable data transfer for free, basically.
Yeah.
HTTP doesn't need to worry about lost packets.
Correct. TCP handles the reliability. Now, a really defining characteristic of HTTP is that it's a stateless protocol.
Stateless, meaning it has no memory.
Precisely. The server treats each request from a client as completely independent without any memory of previous requests from that same client.
That sounds inefficient. How does anything complex work, like online shopping?
Yeah, it does seem counterintuitive, but that simplicity actually made it easier to build and scale web servers initially. The lack of state meant less overhead per client, but yes, it created challenges for applications needing persistence, which led to workarounds.
Okay, we'll get to the workarounds, but first, how did this statelessness affect connections? You mentioned HTTP 1.0 earlier.
Yes. Early web HTTP 1.0 used non-persistent connections. This was a performance killer.
Why?
Because for every single object on a web page, the HTML file, each image, each script, a brand new TCP connection had to be established. Handshake, transfer, teardown, again and again.
Wow, that sounds slow, all that opening and closing.
Incredibly slow, especially with pages having many small images. HTTP 1.1 introduced persistent connections. This allowed the browser to request multiple objects over the same TCP connection, which remained open. Huge improvement.
Much more efficient, like keeping the phone line open instead of redialing for every sentence.
Exactly. Reduces latency, reduces server load.
Okay, so the browser sends requests, the server sends responses. What do these HTTP messages actually look like?
They have a pretty clear structure. A request message starts with a method like get to retrieve something, POST to send data to the server, like filling a form, head to get just the headers, PUT delete for other actions. Then there are header lines.
Headers like?
Things like host, telling the server which website you want, since one server might host many sites. User agent, identifying your browser, accept language, indicating preferred languages.
And the server's response?
It starts with a status line, including the famous status code. 200 OK is success. 404 not found means the resource isn't there. 301 moves permanently. 304 not modified is used with caching.
Right, I've seen those.
And then response headers like content length, telling the browser how big the object is, content type, indicating if it's HTML, an image, etc., and then the actual data, the object itself.
Okay, back to the stateless problem. If HTTP forgets everything, how does Amazon remember my shopping cart?
Ah, the workaround. Cookies.
Cookies, not the edible kind.
Hey, these are small pieces of data that a website asks your browser to store. The site sends a cookie header, your browser stores it, and then sends that cookie back with subsequent requests to the same site.
So the cookie acts like an identification tag.
Essentially, yes. The website uses the cookie value to look up your past activity or session information stored in its own back-end database. This creates a user session layer on top of the stateless HTTP. It allows sites to remember who you are, your preferences, your shopping cart.
Very useful, but also potentially tracking me.
That's the privacy concern, yes. Cookies enable tracking user activity across sessions and sometimes even across different websites, depending on how they're implemented.
Okay, another performance thing. Web caching, how does that work?
Web caches, often called proxy servers, are network entities that store copies of recently requested web objects, like pages or images. They can be located closer to users, maybe within an ISP's network, or even in your browser.
So if I ask for a page, it might come from the cache instead of the original server.
Exactly. Your browser can be configured to send its request to a cache first. If the cache has a fresh copy of the requested object, it sends it back immediately, super fast.
And if it doesn't have it, or it's old?
Then the cache acts as a client itself, requests the object from the origin server, stores a copy, and then forwards it to you.
So it speeds things up and reduces traffic on the main internet links.
Massively. It reduces response time for users and significantly cuts down traffic, especially on expensive international or access links. And there's a mechanism called conditional get, where the cache can ask the origin server, has this object changed since this date? If the server says no, 304 not modified, the cache just uses its stored copy. Very efficient.
Cool. And things keep improving, right? HTTP 2, HTTP 3?
Yes. They address some limitations of HTTP 1.1. One big one was head-of-line HOL blocking.
Head-of-line blocking.
With persistent connections in HTTP 1.1, if you requested several objects over one TCP connection, and the first object was really large or slow to arrive, it could block all the subsequent, potentially smaller objects behind it, even if they were ready.
Like a slow truck holding up traffic on a single-lane road.
Perfect analogy. HTTP 2 fixes this using framing. It breaks down multiple requests and responses into smaller independent frames and interleaves them over a single TCP connection. It's like having multiple virtual lanes on that road.
Much better parallelism.
Much better. It also allows for things like request prioritization and server push, where the server can proactively send resources it anticipates the browser will need without waiting for a request.
In HTTP 3.
It takes things even further, primarily by running over a different transport protocol called QUIC, which itself uses UDP underneath.
Yeah.
QUIC provides encryption by default and handles connection establishment and multiplexing even more efficiently than TCP for HTTP 2's purposes, further reducing latency.
Wow, okay. Constant evolution. Let's switch gears to another application we all use, electronic mail.
Email, a classic asynchronous communication tool. The main components are your user agent, like Outlook, Thunderbird, or the Gmail web interface, mail servers, and the protocol that moves messages between servers, SMTP.
User agent mail servers.
Yeah.
Okay, what's SMTP?
Simple mail transfer protocol. It's primarily a push protocol. When you compose and send an email, your user agent sends it to your outgoing mail server. That server then uses SMTP to push the message across the internet to the recipient's incoming mail server.
So SMTP handles server-to-server transfer.
Yes. An interesting historical artifact is that SMTP was originally designed for very simple 7-bit ASCII text only.
Like plain text. No formatting, no attachments.
Exactly. That's why even today, when you send an email with attachments or rich formatting, that non-ASCII content needs to be encoded into an ASCII format using standards like MANI before SMTP can handle it, and then decoded by the recipient's user agent.
Huh. So SMTP pushes the mail to my server. How do I get it from my server to read it?
Good question. That's a pull operation, and it uses different protocols called mail access protocols. The most common ones are POP3, Post Office Protocol, IM, Internet Message Access Protocol, and increasingly just HTTP itself for webmail interfaces like Gmail or Outlook.com.
So SMTP for sending, IM or POP3, or HTTP for retrieving?
Generally, yes. IM is more powerful than POP3 as it allows you to manage folders and messages directly on the server, synchronizing across multiple devices.
Okay, that makes sense. Now, there's one piece of infrastructure that seems critical for almost everything we've discussed. Finding the right servers in the first place.
DNS.
Ah, yes, DNS, the domain name system. Yeah, absolutely fundamental. You can think of it as the internet's phone book.
Because humans like names, computers like numbers.
Precisely. We prefer easy-to-remember host names like www.google.com, but network equipment needs numerical IP addresses like 172.216.160.142 to actually route traffic. DNS is the distributed system that performs this translation.
Distributed, meaning it's not just one big server somewhere. Definitely not. A single centralized DNS server would be a nightmare. It would be a single point of failure. It couldn't handle the sheer volume of queries worldwide. It would be too far away from many users, causing delays, and it would be impossible to maintain.
Okay, so how is it organized?
It's a distributed, hierarchical database. Think of it like a tree structure.
A tree.
At the very top are the root DNS servers. There are hundreds of these strategically placed around the world. They know where to find the servers for the next level down.
Which
The
is?
top-level domain, TLD servers. These handle domains like .com, .org, .net, .edu, and all the country code domains like .uk, .de, .jp.
So if I look up www.google.com, the root tells me where the .com servers are.
Exactly. Then you query a .com TLD server, and it tells you where to find the DNS server specifically responsible for the google.com domain.
And those are?
The authoritative DNS servers. These are typically run by the organization itself, like Google or its ISP. They hold the actual records mapping host names like www or mail within google.com to their IP addresses.
Wow. So my computer might have to talk to several different servers just to look up one name.
It might. Your computer usually queries its configured local DNS server first, often provided by your ISP. That local server then acts as a proxy, handling these hierarchical queries for you.
How does this whole system cope with billions of lookups every day? It sounds like a lot of back and forth.
2 words. DNS caching.
Ah, caching again.
Massively important for DNS. When any DNS or your local server, a TLD server, performs a lookup and gets an answer, like the IP address for www.google.com, it caches that mapping for a period of time, defined by the authoritative server.
So the next time someone asks the same local server for www.google.com,
It can likely answer immediately from its cache without needing to go all the way back up the hierarchy to the root servers. This dramatically speeds up lookups and reduces the load on the higher level servers.
very clever. Does DNS do anything else besides hostname to IP translation?
Yes, several important things. Host aliasing. A complicated hostname can have one or more simpler aliases. Mail server aliasing. MX, mail exchanger, records in DNS, tells sending mail servers where to deliver email for a domain, which might be different from the main web server. And load distribution. Busy websites often have multiple servers with different IP addresses. DNS can return a rotating set of these IPs for the same hostname, helping to spread the load across the servers.
So it's much more than just a phone book. But being so critical, is it a security risk?
Absolutely. DNS is a prime target. DDoS attacks against major DNS providers, like the DIN attack in 2016 using the Mirai botnet, can take down huge swaths of the internet by making name resolution impossible.
I remember that. Lots of big sites were unavailable.
Exactly. Another threat is DNS poisoning or spoofing, where attackers trick DNS servers into caching incorrect mappings, potentially redirecting users to malicious sites. There are efforts like DNSSC, DNS security extensions, to try and authenticate DNS responses and prevent poisoning, but securing DNS remains a major ongoing challenge.
Okay, one last area, especially for people who want to build these applications. Socket programming. This is where the code meets the network, right?
Precisely. If you're writing a network application, you're writing code that interacts with sockets. You write a client program and a server program, and they communicate by reading from and writing to their respective sockets.
And you choose between TCP sockets and UDP sockets.
Yes, and that choice directly reflects the transport services we talked about. If you choose UDP sockets, you're opting for that connectionless, unreliable service.
The fire and forget model.
Pretty much.
Mm-hmm.
You create a socket, attach the destination IP address and port number to each chunk of datagram you send, and just send it. No prior connection setup, no delivery guarantee, like sending postcards.
And TCP sockets.
They are connection-oriented. Before any application data can be exchanged, a connection must be established between the client and server sockets. This involves that famous three-way handshake.
The handshake.
Yes. The client sends a request to connect. The server acknowledges, the client acknowledges the acknowledgement. Only then is the connection established. The server typically has a main welcoming socket listening for incoming requests. When a client connects, the server creates a new dedicated connection socket just for that client's communication.
So each client gets its own private line, essentially.
That's a good way to think of it. Data sent over this TCP socket is treated as a reliable, ordered byte stream. It's like making a phone call. You establish the connection first, then you have a reliable channel for your conversation.
And the beauty of using sockets, from a developer's point of view,
is that the socket API, provided by the operating system, hides most of the complexity of the underlying transport and network layers. The developer just needs to know whether they want TCP's reliability or UDP's speed, and then they read and write data to the socket. They don't have to manage packet retransmissions or routing details themselves.
It's that layered architecture doing its job. Abstraction.
Exactly. It makes building complex networked applications feasible.
Wow. We've covered a lot of ground today. From the applications we use every day, peeling back to the client-server and P2P architectures, how processes communicate via messages and sockets.
Looking at the crucial choice between TCP and UDP based on needs like reliability and the lack of guarantees for throughput and timing in the standard internet.
Then diving into key protocols like HTTP for the web, with its evolution from non-persistent connections and statelessness to cookies, caching, and modern versions like HTTP 2 and 3.
And SMTP and IMAP for email, and finally the absolutely critical role of DNS as the Internet's directory, along with its hierarchical structure and caching mechanisms.
It really paints a picture of incredible complexity, but also amazing ingenuity that makes all this seamless global communication possible.
It truly is remarkable. Every single click, every stream, every message relies on this incredibly intricate dance of protocols, working across billions of devices, built piece by piece over decades.
And as we saw, especially with HTTP, this application layer is where so much innovation continues to happen, constantly giving us new ways to connect and experience the digital world.
So perhaps the next time you fire up your browser or send a message, you can appreciate that invisible ballet of data just a little bit more. All those processes, sockets, protocols working behind the scenes.
It's definitely more than just magic. Thank you for joining us on this deep dive into the application layer. Keep exploring, keep learning.
And we'll catch you on the next one.